Я нажимаю запись, и можно начинать.
Hello, everyone, and thanks for inviting me to give this talk. I'm going to talk about relational algebras. This talk is rather introductory. That is, I ain't going to prove any technically complicated results. That would be a kind of invitation. So let's have a look at the structure of our talk. First, we discuss Boolean algebras and Stone's representation theorem. Secondly, we have a look at Boolean algebras with operators with some examples. Finally, we discuss how one can algebraize binary relations and discuss abstract relation algebras and their representations. Okay, so Boolean algebras, the first item. Suppose we have some set, non-empty set X, and there are the following well-known operations on the subsets of X, such as union, intersection, and complement. And one may visualize all those operations using Euler circles or something like that. Everybody knows that, as far as I can see. And with every set X, non-empty set X, one can associate a structure that has the form, the power set of X, union, intersection, minus as the complement operation, the empty set as the identity elements for union, and X as the identity elements for intersection. Okay. This is the most essential example of a Boolean algebra, and Boolean algebras in turn allow us to consider, this is misspelling, allow us to consider structures as above. In a more abstract way, let's have a look at the abstract definition of a Boolean algebra. We have structures of this kind, such as B is the carrier of a Boolean algebra plus multiplication minus 0 and 1. Informally, plus stands for union, multiplication stands for intersection. And here are axioms. Both binary operations are associative, commutative, and idempotent. 0 is the identity elements for plus. 1 is the identity elements for multiplication. We have also those absorption laws and the principles that connect plus, complements, and multiplication. In fact, this is a kind of algebraic reformulation of the corresponding axioms of classical logic. And of course, we have this distributivity principle. As you might know, Boolean algebras are connected with classical logic, since classical logic is exactly the logic of Boolean algebras, and one may show that every unprovable formula can be refuted on the free countably generated Boolean algebra, which is the same as the Lindenbaum-Tarski algebra of classical logic. That is, algebras of formulas factorized through provable equivalence. Okay, and here we have a wonderful fact that one can materialize an abstract algebra, an abstract Boolean algebra as some algebra of sets. But for this materialization, we need some ultrafilters. Okay, but before that, we note that every Boolean algebra is a pole set, a partially ordered set, And the ordering relation can be defined in the following way. A is less than or equal to B if and only if A plus B equals B. Now, this is quite essential because if we interpret plus as a union of sets, A is a subset of B if and only if A union B equals B, something like that. Okay, this is the definition of a filter. Let B be a Boolean algebra, and F is a subset of B, a non-empty subset of B, and a proper filter is not set of subsets, but sets is a set. Okay. Forget about this line, please. It's taken from the other presentation. Sorry. Let B be a Boolean algebra and F be a non-empty subset of a Boolean algebra, and F is a proper filter if the following three conditions hold. First, 0 doesn't belong to F, and F is closed under multiplication, or it's closed under intersection, or it's closed under finite conjunctions, if you prefer, and every filter is upward closed. That is, if A is an element of F, and A is less than or equal to B, then B is also an element of a filter. Okay, logically, well, from a logical point.
What is the definition of filter or a proper filter?
Proper.
Do we need to add something to say that this?
No. If we drop the first item, then we have a filter.
Okay. Yeah.
But we require filters to be non-trivial, that don't coincide with the whole algebra. But if 0 is an element of a filter, then this filter is the same as the whole algebra, because 0 is the least element, and this condition and the third condition imply that our filter coincides with the whole algebra. Does it make sense?
Yeah, one terminological question. Proper filter in Russian, it's собственный filter, right?
Yes, that's correct.
Okay, thanks.
And from a logical point of view, well, according to the title of this seminar, filters are consistent theories over the classical logic, that is, set of propositional formulas closed under derivability. And from an algebraic point of view, filters are connected with congruences in Boolean algebras. A congruence on some algebra is an equivalence relation that commutes with all algebraic operations. And from this point of view, filters play the same role as ideals of rings or normal subgroups of groups. Okay. But we need ultrafilters, not just filters. An ultrafilter is a maximal filter. That is, a filter U is an ultrafilter if it has no non-trivial extensions. That is, if U prime extends U, then U is equal to U prime. Moreover, we have the following equivalent definitions of an ultrafilter. These ones, I mean. But the most intuitive definition of an ultrafilter is the third one. If for all elements, for every element of a Boolean algebra, we have either A is an element of an ultrafilter or its negation, but not both. ultrafilters appear everywhere. Algebraic logic, this is our case, topology, metric spaces, model theory, and etc. And logically, an ultrafilter is a complete theory, according to the third definition of an ultrafilter. And algebraically, ultrafilter is the same as maximal congruence on a Boolean algebra. But you have already encountered ultrafilters because every logician encounter complete theories. This is one of the most widespread constructions in logic. So ultrafilters are everywhere, but sometimes they are hidden under the carpet. Okay, so now we are ready to formulate Stone's representation theorem. Okay, let B be a Boolean algebra, define spectrum, the spectrum of B that consists of all ultrafilters over this Boolean algebra, and the spectrum of a Boolean algebra is always non-empty because every filter can be extended to an ultrafilter, assuming, of course, the axiom of choice. I mean, the equivalent version of the axiom of choice called Zone's lemma. This fact has a logical counterpart called the Lindenbaum lemma, but it can be proved without the axiom of choice. But the fact that every consistent theory can be extended to some complete theory is the instance of the fact that every filter can be extended to an ultrafilter. So here we have the following representation theorem. Okay, let B be a Boolean algebra as above, then B is isomorphic to some algebra of sets. Here we have this function h that maps our Boolean algebra to this Boolean algebra. We have power set of a spectrum, with set theoretic operations, union, intersection, and the empty set, and the whole spectrum as the top elements, and show that this function is an embedding. That is, it preserves all operations and it's one-to-one. That is, different elements have different images. This function is arranged as follows. We map every A to the set of ultrafilters that contain this element A. And this Stone representation map generalizes the idea of canonical valuation from canonical models. Okay, so we have an injective function from B to this power set algebra, and thus B is isomorphic to its image in the power set of the spectrum of B. That was Stone's representation theorem. Let us discuss and summarize what we have already done. We showed very briefly by providing a proof sketch that every Boolean algebra can be represented as some algebra of sets. Okay, here we have a kind of materialization of a Boolean algebra. In other words, if we have an abstract Boolean algebra, we can concretize it with its ultrafilters. That's the idea. And we can refine this result and have a look at Stone representation Stone's representation theorem using categories. But don't be afraid of that, because I'm not going to explain the Stone theorem categorically. I just mentioned this fact to have a broader landscape. Okay, and here one can show that the categories of Boolean algebras and Stone spaces, that is compact Hausdorff zero-dimensional topological spaces, are dually equivalent. That is, Boolean algebras and topological spaces of a certain kind are the same thing naturally. Okay, but I mentioned this fact for a broader context. I ain't gonna prove that. Okay. Any questions, or I can go ahead?
What does Hausdorff mean?
Hausdorff, this is a widely used property of topological spaces. It means that if we have two different points from our spaces, from our space, then one can distinguish them from each other with open sets, with open neighborhoods. But zero-dimensional, the zero-dimensional topological space is a little bit more complicated thing. It means that its base is the set of all closed open sets, clopens, and etc. But I really don't want to go into that kind of stuff. It's just a fun fact.
Just one question, maybe it's not like connected strictly to the theme, but nevertheless, there is a fact from model logic when we deal with script key frames that frame validity is preserved under ultra-filter extensions, and it looks really the same as Stone's theorem. So I was wondering, is there any like Boolean algebra connected with model logic dealing with this fact?
I'm going to talk about that a bit later.
Okay.
So, can I go ahead?
Yep.
Okay. So the second topic is Boolean algebras with operators. Here is the abstract definition of an operator over a Boolean algebra, but we concretize our operators by providing some examples. So here is the abstract definition. Let B be a Boolean algebra, then an n-argument function f is an operator if the following holds. The first condition claims that an operator must preserve disjunction in every argument, in every coordinate, and the same for bottom. Okay, this is a more abstract definition of diamond. Okay, if we forget about these guys, then we have fa plus b is equal to fa plus fb. And if we forget about these guys, then we would have f0 is equal to 0. So think of that as a kind of many argument diamond. Okay.
I don't get it. Why is it a diamond?
Huh?
I don't get it. What is the connection with diamond?
Diamond is a one argument operator over a Boolean algebra, because diamonds A disjunction B is equivalent to diamond A disjunction diamond B. and diamond false is equivalent to false.
Oh, yeah, I see. Yeah.
That's what I mean when I was talking about diamonds. But here we have many argument functions, and according to our requirements, an operator must preserve disjunctions in every argument, and the same for the bottom. Okay. Okay. So if fi, where the capital I is some set of indices, is a family of operators, then the structure M with B, a Boolean algebra with this family of operators, is called a Boolean algebra with operators. And if every operator is one argument, then we call such a Boolean algebra with operators a model algebra. Okay.
And can we define box with the help of set operation minus the same way we define box with diamond in model logic?
Box, there is a dual definition of an operator. If we prefer box as a primitive connection, box must preserve conjunctions and the top elements. In other words, box A conjunction B is equivalent to box A conjunction box B, and box true is equivalent to true. But
yeah, but I mean, if we define like this function, will it be like that function which corresponds to diamond? It will be like minus this function A. I mean,
yes.
oh, sorry.
Yes, I think I understand your question. If we apply complements, then we would have a kind of main argument diamonds. But for relational algebras, this definition is more convenient. Okay.
Okay.
So let's have a glance at some examples. The first example is for model logicians. Okay, let F, W, R is a crypto frame where W is a non-empty set and R is an arbitrary binary relation on W. So consider a function R minus 1 that takes some subset of W and returns some subset of W in the following way. We take X, a subset of W, and return those X's, elements of W, such that X sees Y for some Y from X. So we take a subset and return its R predecessors. Okay. And one may check quite directly that R minus empty set is the same as the empty set, and this function commutes with unions. Okay, and also I should say that this operator encodes diamonds in our crypto models. So if we take a crypto model and have a look at the value set of some diamonds A, then this set equals to R minus 1 of the value set of A, a formula that was modelized. That's the rough idea, okay? And thus, this structure where we have the power set of worlds, disjunction, intersection, minus as the complement, empty set as bottom, W as top, and this R minus 1 is a Boolean algebra with the operator, and such an algebra is called the complex algebra of a cryptic frame F that we denote as CMF. This notation is due to Goldblatt's, and this construction connects algebraic and relational semantics with model logic, because one may associate a model algebra with every cryptic frame, okay, and one may associate a cryptic frame with every model algebra, a cryptic frame of a certain kind. We discuss that a little bit later. So, but of course, not only this connects algebraic and relational semantics, but this in particular. Any comments or questions?
And like I assume that this algebra corresponds to just a minimal normal model logic A, right?
Not quite. These are minimal requirements for our operator, but the relation is arbitrary. It might satisfy any conditions, but in the basic case, yes, I agree. It's the algebra of the K logic, but it might be something else. That depends on our relation. For example, if R is reflexive, then we have the third condition, which claims that every X, a subset of W, is a subset of R minus 1X. Okay?
Okay.
So this is the essential way to algebraize our conditions for our cryptic frames, but this is a different topic. I was talking about that just in order to provide an example of a Boolean algebra with operators. So can I go ahead?
Yep.
Right. The second example is from topology and model logic as well. So let X be a topological space. This X is a set of points. Tau is the set of open sets, an arbitrary topological space, and define a function CL that takes a subset of X and returns another subset of X. And it is defined in this way. CLA is the smallest containing set containing A. It is the smallest closed set that contains A. So we take all closed sets that contain A and take its intersection, and we have the closure of A. Very roughly, this operator allows one to make an arbitrary subset of a topological space closed. And of course, CL is an operator, and structures of the form, sorry, X, not W, misspelling, where we have all subsets of points, Boolean operations, and the closure operator, and structures of this form are called topological Boolean algebras, and it is well known that the logic S4 is complete with respect to those algebras. It is the famous Mckinsey-Tarski theorem. And equivalently, I don't want to go into topology in more detail. Closure of a subset is the closure of a subset A denotes our set A extended with the set of all limit points of A. And one can take limit points of A without A itself. And the set of limit points of A is called the derived set of A, and it is due to Cantor himself, as far as I know. And taken derived sets, not derived, not deriving, but derived. Taken derived sets also introduces a model operator, which is also well studied in topological semantics and probability logic, because diamonds and the logic GL is essentially a derivation modality. And again, here one may have a look at the paper by Lev Beklemishev and David Gabelaya about topological semantics of probability logic. So, and again, I mention all those examples to have a broader, a broad context and landscape of operators of the Boolean algebras. So, do you have some questions?
No, I think we can go ahead.
Yes. So, the third example is closer to our topic. Okay, so let X be a non-empty set, and Y is a set of binary relations of X, arbitrary relations. So here we define a binary relation on Y, the relational composition, and here we assume that Y is closed under this operation. Otherwise, this definition makes no sense. Okay, semicolon. This semicolon R1 semicolon R2 is the set of all pairs XY such that there exists Y of X with this condition that XY is an element of R1 and YZ is an element of R2, not R1. Sorry, another typo. We have quite an essential binary operation on binary relations. So if we have two relations, then one can take its compositions, its composition. Sorry, and this operation, as I have already said, is called the relational composition, and the relational composition is also an operator because it preserves unions and empty sets in each coordinate. Okay. A ridiculous example: let X be a set of some people, and then formally we have a binary relation X parent of XY that we informally read as X is a parent of Y. Then we can introduce the binary relation grandparent of as the composition of parent of with itself. Does it make sense, or I need to explain stuff in more detail?
No, it's clear. Thank you.
And another thing that I want to mention, that one may also interpret relational composition as a kind of temporal binary modality. If we interpret composition as a sequential composition of actions, okay, one may read Zx as Z is a result of X, then relational composition is a sequential composition of actions, and moreover, this is an example of a non-Boolean binary connective, if we read that as a modality, which is non-commutative, clearly, because sequential composition of actions is non-commutative. Here is my favorite example. From the one hand, one may give a talk at this seminar, for example, and have a couple of drinks with your friends, and they will tell you that was a great job, cheers, mate, and etc. Alternatively, of course, one may have a couple of drinks and give a talk afterwards. But frankly, I've never tried the second way, but the result might be slightly different. But I wouldn't try the second way, but because I would give talks being sober. So, the importance of being sober is not the single reason for which we study the relational composition, because one needs to have a look at relation algebras. The second example is related to converse relation. Okay, let X, as above, be a non-empty set, and Y a set of binary relations on X. And so the following operation is also an operator. If we have a binary relation, then one can take its converse. In other words, the converse of X consists of those pairs XY such that YX is an element of R. For example, we take the relation, I don't know, for example, I have a couple of examples. Child of is the converse relation of the relation parent of. If my father is my father, then I'm a son of my father. I have no better examples, sorry. The more curious example, perhaps, is the following one. Suppose we have an ordering relation on the set of natural numbers, integers, rational numbers, real numbers, but not complex numbers. Then the relation is less than is the converse of the relation is greater than.
Sorry, may I ask a small question about the first example, child of and parent of? Is it important that you have only one father, but father can have many children? Is it important here or not?
It's not important because we have only binary relations, and those relations don't have to be functions. So
yeah, that was my question. So we do not talk about all functions are operators, but operators are not functions, and etc. Yeah.
Yes, taken converses is an operator, but binary relations are not functions. An operator is a function, but but an operator is a function which is applied to binary relations.
I see. Thank
you. Composition and taken converses are algebraic operations on binary relations. Does it make sense?
Yes. Yes. Pretty sure.
Okay. And we have the Johnson-Tarski theorem. We are done with examples. First of all, I would like to extend Stone's theorem for Boolean algebras with operators. Okay. My point is to show by providing a sketch that one can represent Boolean algebras with the operators using ultrafilters as well as Boolean algebras. let M be a Boolean algebra with operators, then the ultrafilter frame of M is a relational structure which has the form spectrum of M, the set of ultrafilters, and family of binary relations. Here we assume that all our operators are unary for simplicity. So we have unary operators, and we associate with them binary relations. Okay, but if we have an n-ary operator, then we associate with it n plus 1, but n plus 1. Okay, let me reformulate that. If we have an n-ary operator, then we associate with it a relation of arity n plus 1. Okay, so in particular, we associate binary relations with unary operators, diamonds. Okay, so let us define these, to be honest, binary relations in the following way. And all those relations are labeled with the same set of indices as our family of operators, because our binary relations encode our operators. This is the point. Okay, and so let's have a look at the definition of a binary relation on the set of ultrafilters. So we take some I from the capital I and two ultrafilters, and U1, an ultrafilter, sees the ultrafilter 2 by a relation Ry, Ri, don't know how to pronounce this properly. Ri, yeah, yes, that's correct. The ultrafilter U1 sees the ultrafilter U2 by a binary relation Ri, if and only if we have the following story. If we apply this operator Fi to every element of an ultrafilter U2, then the result of this application has to be a subset of an ultrafilter U1. This definition looks rather abstract, but the definition of an ultrafilter frame is a kind of generalization of a canonical frame. Okay, because this exactly the definition of a relation between complete theories in the canonical frame of some model logic. Okay, does it make sense? Or I have to explain this definition in a more clear way? Or you have some remarks?
So it's like if any ultrafilter corresponds to a complete
maximal consistent.
Yeah, maximal consistent set, then this ultrafilter frame will correspond to a canonical frame from Kripke frames.
Yes, that's correct. That's correct. But a canonical frame is a frame of countable theories. But here, the cardinality of a Boolean algebra might be arbitrary. It might be uncountable. But the standard definition of a canonical frame assumes that we have maximal consistent theories. These are countable sets of formulas, which is equivalent to the fact that we have the ultrafilter frame over a countable Boolean algebra with operators. In other words, the ultrafilter frame of a countable Boolean algebra is the same as the canonical frame. The same, not the same precisely. Okay.
And without this remark, I mean, like ultrafilters may be even uncountable.
Yes, because we would take an arbitrary algebra of an arbitrary cardinality.
Okay, it makes sense.
Okay.
I think we need to define a canonical relation in terms of diamonds. Yeah.
Yes, yes, we define canonical relation in terms of diamonds.
Yeah.
The definition of a canonical relation in terms of boxes is more widely used, but this definition is closer to the definition of an operator on a Boolean algebra. That's why I prefer this variant of definition of this relation, which is the canonical relation in particular. The canonical relation is the instance of this kind of stuff. Okay, and we have the canonical extension of a Boolean algebra with operators m, which is that we denote as m plus, which is the complex algebra of its ultrafilter frame. We have already had a look at complex algebras. That was the first example of an operator of a Boolean algebra, and we take the ultrafilter frame, associates a Boolean algebra with operators taken from the ultrafilter frame and obtain another Boolean algebra with operators. Does it make sense? And here we have the Johnson-Tarski representation theorem proved in the paper called Boolean Algebras with Operators, published in 1953 or 4, can't remember. That every Boolean algebra with operators m embeds to its canonical extension. So as above, we have the function m that maps m to m plus, the canonical extension of m, and we have the same stone map. We map every element to the set of ultrafilters that contain A. One needs to check that this operation as above commutes with Boolean operations. It's one-to-one, that is, different elements have different ultrafilters, and the key observation is that our stone representation commutes with operators. That is, a representation of FIA is the same as FI applied to all those filters, all those ultrafilters that contain A. I ain't gonna prove that, but one may have a look at the book by Venema, Blackburn, and Deriker called Model Logic. As far as I remember, the fifth chapter or sixth chapter or even seventh chapter, can't remember, where this fact is proved quite accurately, but I'm going to drop that. And of course, if we take a countable model algebra of a certain kind, take its canonical frame, and then this map, some representation, is exactly the canonical valuation of formulas. Okay. Does it make sense?
What is the meaning of the arrow? The first
Which
one,
arrow?
generated submodel?
No, this arrow denotes embedding.
Embedding from any algebra to its canonical extension, right?
Yes, that's correct. If you are interested in that kind of stuff, you may have a look at two papers that I mention quite often. The first paper is called Varieties of Complex Algebras by Robert Goblet, and the second is a survey of Boolean algebras with operators written by Bjarne Johnsen, the co-author of this representation theorem. In fact, this construction is a little bit more abstract version of the construction of a canonical frame. And again, canonical frames and so representations of Boolean algebras with operators are strictly connected with each other. Because maximal consistent theory is the instance of an ultrafilter. Okay. So can I go ahead?
Yep.
And moreover, there is the dual equivalence between categories of Boolean algebras with operators and topological cryptic frames, or according to the alternative terminology, general descriptive frames. It's due to Robert Goblet and Leo Issaquet. Leo Issaquet provided topological duality between Heightened algebras and S4 algebras. He proved that Heightened algebras and S4 algebras, I mean, their categories are equivalent to categories of stone spaces with relations, and the more abstract version of this duality is by Robert Goblet. If you are interested in that kind of stuff, then you might have a look at the paper by Goblet called Metamathematics of Model Logic. And again, this is a refinement of the Johnsen-Tarski representation theorem, because one may show that Boolean algebras with operators is roughly the same thing as cryptic frames with the additional topological structure, the structure of a stone space, to be more precise. So from this point of view, this duality makes relational semantics and algebraic semantics equivalent. But relational semantics is more helpful for applications such as knowledge of rational agents or something like that. I don't have to explain this kind of stuff for this audience, as far as I understand. So can I go ahead?
Yep.
So the main topic of our talk is relational algebras and their representations. We're going to have a look at representations of a different kind. One can represent any relational algebras with its ultrafilters as above, but we are interested in representations of a different kind. All those operations, such as compositions and taken converses, allow us to algebraize binary relations. So here we consider a particular kind of Boolean algebras with operators called relational algebras. Don't mix that with relational algebras from relational databases. This is a different story. Relational algebras, that is Boolean algebras with converses, compositions, and the constant elements that denotes the identity relation. So let me be historical for a minute. So that relational algebras have been introduced by Alfred Tarski in the 1940s for some mathematical purposes, but I don't know the historical context in more detail. So I know that as a fact that Alfred Tarski was interested in algebraizing mathematics, and he also introduced cylindric algebras for similar purposes. But I'm going to talk about cylindric algebras because this deserves a different talk, perhaps for the same seminar, if you stay alive after this kind of stuff. So first of all, let's have a look at proper relational algebras first. When we were discussing Boolean algebras without operators, then we introduced some operations on subsets. And similarly, we introduce structures with some operations on binary relations, some concrete binary relations. So let U be a non-empty set, a base set. Then a proper relational algebra is an algebra of this form, or relation set algebra, according to the alternative terminology. So here A is some set of binary relations, which is closed under Boolean operations, compositions, and taken converses. A is the equivalence relation on U, which is the top elements of A. In particular, it might be the universal relation. It might be coincide with U times U, but generally this is some equivalence relation which has be a top element of A.
I'm sorry, shouldn't it be that A is a subset of a power set of U times U if it's a set of relations?
Yes,
but not...
yes, that's correct. It has to be a subset of power set of U times U. Sorry. Yes, this is another typo. It has to be a subset to power U times U, not just a subset of U times U. Okay. 1 prime is the identity relation, the diagonal relation restricted to the carrier of our relation set algebra. So we have some sets. We have some set of binary relations. I'm sorry, and it has to be closed on the intersection union. It contains the empty set as the empty relation. It has some top elements, which is some equivalence relation, and this set has to be closed under composition and taken converses. Okay, does this definition make sense? So PRA is the class of all proper relational algebras. So here's an example, a famous example called the Points Algebra. We have the set of rational numbers and the set of relations such as is less than is greater than is less than or equal to is greater than or equal to the empty relation, equality, non-equality, and the diagonal relation that consists of all pairs of rational numbers. So the algebra consisting of these 8 relations forms a relational algebra. This is a famous example because it's widely used in literature about relational algebras. So that means that this set is closed under composition. Okay, for example, the union of this guy and this guy is this guy. Composition of less of this guy with itself is equal to the relation is less than, because the ordering relation on rational numbers is transitive and dense, and etc. Okay, does this example make sense? Or I can go ahead. I hope you are alive. I sincerely hope that you get the point. So here we start with some concrete algebras of binary relations with compositions, composition taking converses and the identity relation. Okay, and we have the class of all proper relational algebras, the class of all concrete algebras of binary relations, PRA. Okay, does it make sense? Can I go ahead?
Yep.
So here is the abstract definition of relational algebra as a kind of Boolean algebra, as a kind of Boolean algebras with operators. A relational algebra is an algebra that consists of these operations and constants, where A plus multiplication 0, 1 is a Boolean algebra. So this structure obeys the same axioms as above. A with the composition and 1 prime is a monoid, that is, composition is associative, that is, A composition B, A composition B taken in brackets is the same as A composition B composed with C. So these are the same guys. That's what the associative law means. Do you get that? And 1 prime is the identity elements for composition. That is, for all A composition 1 is the same as 1 composition A is the same as just A. So here I reformulated this sentence claiming that A composition 1 prime is a monoid. And the operation of taking converses is involutive, and it's quite essential because we take a binary relation, take its converse relation, and take a converse relation of a converse relation, and it has to be the same relation. Okay.
And like once again, plus corresponds to composition of relations, and multiplication corresponds to intersection of relations, right?
Plus denotes union of binary relations. Multiplication is intersection, as above when we were discussing Boolean algebras. semicolon denotes composition, and 1 prime denotes the identity relation. Okay.
And what? Just one, not 1 prime. What is it?
Is the top element, the identity for intersection, as in Boolean algebras.
Okay, and if I'm not mistaken, it was like 1 is an equivalence relation, right?
Yes, in order to make these top elements and so on. But we actually don't need that for our further examples, but generally it has to be the top relation of our algebra of binary relations, so it has to be equivalence relations. Intuitively, the top elements of relational algebra is the union of all relations that belong to our relational algebra, but but our carrier of a relational algebra is closed under composition. It contains the diagonal elements, and it's closed under taken converses, and that makes the top relation of a relational algebra an equivalence relation, because being closed under composition implies transitivity. Being closed under taken converses implies the symmetry property, and having the diagonal relation implies reflexivity. That's the idea, and that makes the top elements of a relational algebra an equivalence relation.
Can we think about the 0 prime binary relation? So bottom element, and can we build something like Boolean relational algebra? Is it possible to think about it?
I don't get your question.
Zero prime binary relation, such relation that it gives itself. So not identity relation, but something like destroying element.
Yeah, empty relation.
Empty relation.
Yeah. Can we think about it?
We already have the empty relation from the definition of a Boolean algebra. We have the empty relation, which is the smallest relation in our relation algebra.
Yeah. So we can't have it. Okay.
Yes, we already have it, because we have a Boolean algebra, and every Boolean algebra has the bottom.
Okay. Thank you.
But maybe we can get somehow the least non-empty relation in A.
Not always. We have a look at that a bit later. The minimal non-zero element is called an atom of a Boolean algebra or relational algebra, and if every element has an atom beneath this element, then an algebra is called atomic. But not every Boolean algebra or relational algebra, not every relational algebra has to be atomic. But in our examples, we're going to consider atomic relational algebras with atoms.
Okay.
I have a question. How much time do I have?
You have about 15 minutes.
15 minutes.
Mm-hmm.
Oh, the classical
You can split your talk in 2 parts. You can go ahead.
That would be a little bit better, I guess. because we discuss only 15 slides of 32 slides. So let me stop with some points when it makes sense to stop. Let me finish with the definition. So taken converses commutes with the plus, that is, taken converses commutes with unions, and taken converses commutes with composition, but it changes the order of our arguments, and also plus commutes with the composition in this way.
Could you please clarify the sort operation this in the second column?
Second, this one.
In second column, the third one.
This one.
Yeah, it looks the less intuitive.
Yes, and I would have a look at this axiom in a bit more different way. But this is the topic for further slides. So we have a look at that a bit later. So we have this notation. Array is the class of all relational algebras. Array stands for relational algebras. I believe it's quite clear. And we have this in equation that connects ordering, complements, converses, and composition. And this is the axiom of array, but one can reformulate this principle in a little bit more intuitive way. I will try to explain that clearly, but okay, let me try. One can equivalently replace this in equation with this equivalence called the Peircean law. Here we use less operations in contrast to this item, so it might be a little bit more clear for you. So let ABC be arbitrary elements of a relational algebras. Then we can have a look at some triangles, like these ones. So these triangles are equivalent to each other, and every three elements of a Boolean algebra are connected with each other using one of these equivalent ways. Okay. Let me reformulate that in a more simple way. I believe that these triangles require more explanations, and 10 minutes or 15 minutes might be not enough for that. So I would stop with those triangles and go ahead next Friday.
Okay, could you please explain the name of this law, why it's in terms of Peirce? Are there any connections with standards Peirce law? I mean, the Peirce formula.
I don't know why it's named after Charles Peirce, but as far as I know, Charles Peirce was into analyzing some properties of binary relations independently of Augustus de Morgan. So perhaps he invented those triangles somehow, and those triangles are named after him subsequently. But I don't know. I haven't had a look at Peirce, at works by Charles Peirce, so so my answer is based on some general considerations. I don't know how to answer your question precisely. But let me finish with the intuitive point that in our case, when we consider finite algebras, all those triangles allow us to define composition uniquely. Okay, and we cannot, we might not define composition by providing a kind of multiplication table for every two elements. That's enough to provide the set of triples that which are behaved properly, and extract the definition composition of a composition from those triples. And such triples might be extracted using those transforms called the Pearson law. That's why we use those triangles.
My question is about graphical notation. How is it possible to show that something is equals to 0 in a graphical way?
Here we, you may read these equations directly, that composition of A and B from the one hand and the converse of C do not have common elements.
Oh, okay. Mm-hmm.
So interpret multiplication as intersection, composition as composition, this guy as taking converses, and this, and all those equations claim that the corresponding relations have no common elements, have no common ordered pairs.
Okay. Okay, it's time for short questions and remarks.
So 0 here, can it be, maybe we can talk about 0 prime here, not 0, not
We
0
have-
in the
We
previous.
don't have 0 prime.
We have no 0 prime. We have only 0 without any primes. And 0 stands for the empty relation.
So, yeah, empty. So this is not an element, and this is 0 is a binary relation here.
0 is a trivial binary relation
Trivial binary relation.
that contains no any pairs of elements.
Yeah, I got it. Yeah.
So I would start with the explanation of this principle in more detail next Friday. If you have some intermediate questions, so go ahead. And before finishing, I would overview what we're going to discuss next Friday. Forbidden and consistent triples that we extract from the pairs and transforms of elements, and this allows us to define composition, the definition of a representable relational algebra, that is a relational algebra that can be represented as algebra of binary relations. And we have, and clearly every representable relational algebra is a relational algebra, but the converse inclusion does not hold. So we have a relational algebra which cannot be represented as an algebra of binary relations. Okay, here we have a counterexample of a non-representable relational algebra. Okay, and we overview some negative results. After that, we introduce back and forth games for atomic relational algebras in order to characterize representable atomic relational algebras. we discuss games for them. In such a game, Abelard and Eloise are building some directed graph whose edges are labeled with the atoms of our algebra. Okay, and the definition games and networks or directed graphs with labeling approximate the representation of a relational algebra. And here we have this criterion that if Eloise has a winning strategy in such a back and forth game, then our relational algebra is representable. That is, it can be represented as an algebra of binary relations, and so we can extract this algebra of binary relations from the presence of a winning strategy, because Eloise has a winning strategy if she can build a proper network that gives us a kind of proper condition to make an algebra representable. Okay, and finally, we realize why the Mckinsey algebra, an example of a non-representable algebra, is non-representable by showing that Abelard has a winning strategy in a game over this algebra, and the game is quite short. It has only five rounds. Some references finally, and this is it. Okay.
Okay. Thank you very much. Do we have any short questions or comments? Okay.
I may have a question, but I guess it's way too general. But nevertheless, we have looked at some examples of algebras which corresponds to certain logics. Like we may look at this like algebraic semantics. But I was wondering what's the motivation to introduce this other semantic. Like, do we win something, for example, in terms of complexity, or it's just another semantics? And basically, my question is, what's the motivation of using algebraic semantics instead of more classical ones like relational semantics?
The problem is that algebraic semantics is a stronger version of semantics for every logic, for intuitionistic logic, for modal logic, for, I don't know, relevant logic, paraconsistent logic, or something like that, because we have the uniform completeness theorem for every equational theory. An equational theory is an algebraic counterpart of logic, and if we are interested in modal logic or temporal logic, then there are examples of consistent modal and temporal logics which are cryptically incomplete. They are consistent, but they are incomplete. And so you might have a look at some examples of incomplete logics in the book by Robert Goblet again. The book's called Logics of Computation and Time. You can Google it quite simply. And to make those logics complete, one needs to have a stronger definition of a cryptic frame. And this strong version of a cryptic frame is the same as the definition of a Boolean algebra with operators if we if we keep in mind the representation theorem for Boolean algebras with operators and categorical duality between general descriptive frames from the one hand and the category of model algebras from the other hand. And again, you may have a look at the book by Goblet, Logics of Computation and Time, and the paper by Goblet that I have already mentioned. The paper is called Metamathematics of Model Logic.
Sounds fascinating, thanks.
Okay.
And then could you please say something about Sahlqvist equations? It looks like very interesting topic.
Sahlqvist equations?
Yeah.
Yes, one may consider Sahlqvist formulas from model logic, and one may consider all those Sahlqvist formulas in a more abstract way by considering Sahlqvist equations. Well, any formula from model logic, for example, a theorem or axiom, is naturally an equation. And we reformulate this Sahlqvist stuff in terms of equations and consider Sahlqvist theory for abstract Boolean algebras with operators.
Is it a generalization of Sahlqvist results?
Well, not quite. Not quite. This is a more abstract formulation of the Sahlqvist theorem, but I wouldn't say that this is a generalization, because we need Sahlqvist stuff not for only model logics. We need Sahlqvist stuff for relational algebras, perhaps, or for cylindric algebras, or for other kinds of Boolean algebras with operators. The point is that one may reformulate Sahlqvist results in purely algebraic terms.
Okay, thank you.
That's not quite generalization. Generalizations of Sahlqvist's results is a different story. For example, you may have a look at the PhD thesis by Stanislav Kickert,
Yeah.
a former student of Valentin Scheckman.
Okay, so thank you very much. Let's thank our speaker.
Okay. Hello, everyone, and thanks to attending this talk. And let me continue. But before that, let me remind you what we discussed last Friday. In particular, we discussed Boolean algebras as algebras of sets, of algebras or algebras of unary relations. We defined abstract Boolean algebras, and after that, we discussed Stone's representation theorem, according to which every Boolean algebra can be kind of materialized as some algebra of sets, and this construction requires ultrafilters and something like that. After that, we had a look at Boolean algebras with operators. An operator on a Boolean algebra is a function that is an n-argument function that preserves sums or disjunctions and zeros in every argument. Okay, this is a kind of abstract formulation of a model algebra. Okay, and we had a look at some examples related to Kripke frames, topological spaces, for example, the closure operator, or the derivation modality, and etc. Other examples were related to our particular topic, such as the relational composition, the converse relation. All those operations are operators in terms of our definition. Okay. After that, we discussed how one can extend Stone's representation theorem for Boolean algebras with operators, and introduced the construction called the ultra-filter frame of a Boolean algebra with operators, a kind of more abstract version of the canonical model from model logic. Okay, so here is the Johnson-Tarski representation theorem, according to which every Boolean algebra with operators embeds to its canonical extension. I remind you that the canonical extension of a Boolean algebra with operators is the complex algebra of its ultra-filter frame. And we also discussed quite briefly the dual equivalence between the categories of Boolean algebras with operators and topological Kripke frames, or alternatively general descriptive frames. Those notions are equivalent. Okay. Now, so let me get back to relational algebras. We considered the relational composition and taken converses as operators. So here we have a look at the particular kinds of Boolean algebras with operators called relational algebras, algebras of binary relations, and those algebras have been introduced by Tarski in 1940s for some metamathematical purposes, but historically the first researchers on relational algebras are Augustus de Morgan and Charles Peirce. But to be honest, I'm not so strong in the historical kind of stuff, so I cannot tell you what the particular contribution of de Morgan and Charles Peirce, but I believe you may have a look at some historical literature about that. So we, as far as I remember, we discussed proper relational algebras. That is informally concrete, perhaps, algebras of binary relations. Oh, this is a typo that I didn't fix from the previous time. A is some set of binary relations on U, such that A is closed under Boolean operations, composition, and taken converses. E is the equivalence relation, the top elements of A. The intuition is that E is the union of all relations that belong to A, and this E also has to be an element of A as the top elements. But why is this an equivalence relation, you might ask me? That's because the carrier of this algebra is closed under composition, and this gives us transitivity. A also contains the identity relation, and that gives us reflexivity and etc. So this is an equivalence relation, and PRA is the class of all proper relational algebras of some real binary relations. Here's an example. The Points Algebra, which is widely used for miscellaneous purposes, is the Point Algebra. The algebra of relations on the set of rational numbers, and all those relations are taken from the ordinary relation on the set of rational numbers, and we have a look at that algebra a bit later in a different context. So now we define abstract relational algebras as a kind of Boolean algebras with operators. I decided to reformulate that definition. It's a little bit different if you compare that from that with the definition that I gave last Friday. I believe this definition is a little bit more intuitive. Okay. A relational algebra is an algebra where we have a Boolean algebra. The carrier of a relational algebra forms a monoid under composition and the identity relation. The operation of taking converses is involutive, that is, double application of this operation returns the original elements, and this operation also distributes over finite suprema over disjunctions. It also distributes over composition, but it changes the order of arguments, and this principle claims that relational composition is a kind of binary diamonds. That is, it distributes over disjunction in the following way. Okay. Array is the class of all relational algebras. As you might have noticed, here there previously was an equation, but this principle is a little bit more intuitive as far as I believe. This axiom is called the Pearson law or the Morgan-Tarski law. I don't know which version is more correct. So we have these equivalences between these equations that connect, in fact, Boolean intersection with composition. We have the connection of composition with disjunction, but here is the connection between composition and intersection. We have the following equivalences between these equations, and we have in fact 6 equations, because from this this axiom and other axioms of array, we also have another equivalent equations. So we have this is equivalent to this is equivalent to this, and this is equivalent to this, and etc. And formally, every triple of elements of a relational algebra are always connected with each other by those equivalent equations. One may visualize all those equations using the following triangles. Well, let me remind you how one has to read that. If we take the composition of A and B and the converse of C, then there are disjoints if and only if all those versions are disjoint as well. In other words, every such a triple is closed under all those rotations and taking symmetries. But we need this principle in the technical purpose. So let's have a look how those principles behave in atomic algebras. I believe this law might become more clear if we take a look at atomic algebras. So but before that, let me remind you the definition of an atomic algebra. In Boolean algebras, as well as in Boolean algebras with operators, an atom is a minimal non-zero element, and a relational algebra, as well as Boolean algebra, as well as any other Boolean algebra with operators, is called atomic if for every element of an algebra there exists an atom between there exists an atom beneath there exists an atom C beneath B. Okay, this is a typo. This sentence is badly written. Let me reformulate that. An atom is a minimal non-zero element. I have already said that, and an algebra is called atomic if for every element B there exists an atom C beneath B. That is, every element dominates some atom. So this is the idea. And in atomic algebras, every B has this form. Well, here we assume also that, for simplicity, that our algebra is finite. Every B is equal to supremum of all atoms, where C is an atom such that C is less than or equal to B, not A. Sorry, another typo. It seems I wasn't writing this slide carefully. We define some relations between atoms. So here we assume also that A, B, and C are atoms. Then a triple is inconsistent if the converse of C is less than or equal to its composition, is less than or equal to the composition of A and B. Otherwise, if this doesn't hold, ABC is consistent. I know this looks rather abstract, but I want you to be patient because it's quite clear for atomic algebras. Okay, the Pearson transforms of ABC are triples, ABC, BCA, CAB, and something similar for conversions. That is, the Pearson transformations is rotations and symmetries of this triple, similarly to this picture. But sorry, too much text, but never mind. If a triple is inconsistent or consistent, so are its Pearson transformations. And for atomic algebras, this allows us to define composition on our algebra by providing its consistent triangles. Since the Pearson law is equivalent to this guy, C is less than or equal to A composition B, where C, A, and B are atoms. Well, to be more precise, we have this. C is less than or equal to the composition of A and B if and only if the intersection of C and this composition is non-empty for atoms A, B, and C. That is, one may forget about defining composition by providing its kind of multiplication table. That's enough to provide triples which are inconsistent. And in the case of atomic algebras, a triple is inconsistent sorry. A triple is consistent if and only if the third element of a triple is less than or equal to the composition of A and B. That's the only thing we need for our further conversation and discussion, I would say so. So the moral is that to define composition for an atomic relation algebra, that's enough to provide those triples of elements for which this an equation holds. That's the only thing we need. And in fact, we cannot, one may drop all those abstract stuff with triangles and consider only those triples for which there's an equation holds. Does it make sense? I know it might sound rather complicated, so please ask me some questions. But the only thing that we're going to use is this. But this is a consequence from the Pearson law. That's why I decided to emphasize this place in more detail. Or I can go ahead.
Yep.
Okay. So the only thing that we need is this, and this idea is widespread in algebra because this idea is somewhat similar to a presentation of a group by providing its generators and relations between them. So this somewhat close to group theory, in fact. So let's have a look at consistent triples or consistent triangles, as they often called. Let's have a look at consistent triples of the Points Algebra. The algebra of relations on the set of rational numbers. The Points Algebra is generated by three atoms, is less than, is greater than, and one prime, the multiplicative identity, that is the universal relation on the set of rational numbers, where is less and is greater are mutually converse. Because A is less than B if and only if B is greater than A. That's why these relations are mutually converse. And the composition, one may define the composition by the following table. And one may check quite directly that first, this composition is well defined, that is, it obeys the axioms of relational algebras, and this definition makes sense as operations on relations defined on the set of rational numbers. And the consistent triangles are are all those transformations of the following relations, such as is less, and is greater than is a consistent triple, not triangle. Consistent triple sounds a bit better. Well, just because is less than is a subrelation of the composition of the relation is less than with itself. Well, just because the ordering relation on the set of rational numbers is dense. And for every atom X, we have the following story. The universal relation is a subset of the composition of atom X with its converse. Well, for example, let's instantiate X with this relation, then is greater than composed with this relation with its converse is equal to 1 without prime. Sorry, I said that was quite wrong. This relation is the identity relation on the set of rational numbers, not the universal relation. But this one without prime is the universal relation. Okay, so the identity relation on the set of rational numbers is a subrelation of this relation composed with its converse. As we can see that on the multiplication table, the composition of the relation is less than with the relation is greater than is equal to 1, the universal relation. And one may check that it's true quite directly. So but the identity relation is a subrelation of the universal relation, because the universal relation is actually the full Cartesian product of the set of rational numbers with itself. And we have no other consistent triples, and one can forget about this multiplication table. Take only these triples as well as its transformations or transforms, that would be more correct. I mean, all those symmetries and triangles, and restore this multiplication table uniquely. That's the idea of all those triangles. And it works quite good for atomic algebras and for finite atomic algebras in particular. Does it make sense? So I was trying to explain the role of all those consistent triangles by providing a particular example of a concrete relation algebra. So if you have some questions, so please do ask me about that.
Is it the case that if we have some inconsistent triples, they won't be interdefinable in the same manner, and that's why we need these consistent triples?
Yes, we have. So suppose an algebra is generated by some finite set of atoms, okay, and we provide the set of consistent triangles. The set of consistent triangles is a subset of the set of all possible triples, but we have some consistent triangles or triples, but the rest ones are inconsistent. But so, and conversely, one may provide inconsistent triangles, but the rest ones are going to be consistent. So there are, interdefinable.
Okay.
More questions or comments? Or I can go ahead. Okay. So that's, I believe, the most important definition in my talk. A relational algebra is called representable if there exists a proper relational algebra over some base set such that A is isomorphic to B. That is, there exists a function f such that f is a bijection between A and B, and this bijection commutes with Boolean operations and constants. That is, we have a Boolean homomorphism. Second, our function represents our non-commutative multiplication, a kind of non-commutative multiplication, as the real composition of binary relations, and the same for taken converses and the identity constants. So informally, a relational algebra is representable if it is materializable with some algebra of real binary relations. For example, the point algebra is representable because we can take all those relations, consider them as abstract atoms, define composition using the multiplication table, or we can provide consistent triangles. That makes no difference, and one may prove directly that this algebra is representable over the set of rational numbers as a base set. So previously we had an example of a representable relational algebras, and RRA is the class of all representable relational algebras that we define as the closure of PRA, the class of proper relational algebras, under isomorphic copies. So do you have an intuitive understanding of what the closure of isomorphic copies is, or it's intuitively clear? That is, we have some class of algebras, and those algebras are isomorphic to some other algebras, and we extend the original class with the algebras that isomorphic to some algebras from the original class. For example, one may consider the class of all free groups, but we know that the free group with one generator is isomorphic to the additive group of integers. So the closure of free groups under isomorphic copies is going to contain the additive group of integers as well, for example. That's how taking isomorphic copies works. Does it make sense? Okay, if we consider an arbitrary representable relational algebra that is an element of RRA, then one may observe that every representable relation algebra is a relation algebra in terms of the previous abstract definition. But what about the converse inclusion? If the converse inclusion was true, then we would have the representation theorem, according to which every relation algebra would be representable, that is, materializable with some concrete binary relations. But unfortunately, that's not true. We have counterexamples of non-representable relation algebras. So here's an example. The algebra is called the Mckinsey algebra. It's generated by 4 atoms, 1 prime, A, the converse of A, and sharp. And it is defined by the following consistent triples. But I'm going to discuss this algebra right now because we realize why is this algebra is non-representable using back and forth games.
I have a short question about the previous slide. The previous. Yeah. No. Yeah. Point number 3. Should we change the order of y and x in this outline?
Oh yes, thanks.
Yeah.
Y, x is an element of this product such that xy is an element of FA. So
yeah.
This is a typo, another typo. Sorry for being so absent-minded. So the Mckinsey algebra, so this is an abstract definition by providing some consistent triples. This is a technical example that would allow us to ensure that not every relation algebra, that is algebra that obeys axioms of array, is materializable with some real binary relations, but we realize that using games. But before introducing games, I would have a look at some negative results. Well, in contrast to Boolean algebras, relation algebras are badly behaved. One may consider Boolean algebras as algebras of unary relations because every unary relation is some subset of a set. So, one may think of Boolean algebras as algebras of relations, but unary ones, not binary. And Boolean algebras as algebras of unary relations are, well, they behave pretty good because we have the representation theorem with ultrafilters. So it's not constructive, but anyway, we have represent every Boolean algebra with some unary relations, and we have some quite good algorithmic results related to decidability of equational theory of Boolean algebras, and that's the same as decidability of classical propositional logic, so and etc. But relation algebras are badly behaved because there exist non-representable relation algebras. Our array is a variety, that is, it can be axiomatized with some identities, but it's not finitely axiomatizable, and the equational theory is undecidable, and moreover, our array is not finitely axiomatizable in first order logic. Representability, this is a more recent result, is undecidable for relation algebras. It's due to Robin Hirsch and Hodgkinson. That is, we have no algorithm that would determine whether a given relational algebra is representable or not, and etc. Well, at least this class RRA is elementary, that is, it is axiomatizable in first order logic, and its elementary theory has an enumerable axiomatization, but it's not finitely axiomatizable. We have non-representability, undecidability, the absence of finite axiomatizability, and etc. So, the moral is that we cannot characterize the class of all representable relational algebras with some finite set of identities, or even with some finite set of first order sentences. So that's why we consider some weaker versions of relational algebras, because they might behave better, but this is my topic in relational algebras as well, but this deserves a different talk. But the problem of negative results is that they make us quite sad, because we cannot do some nice things, for example, extracting a finite axiomatization of some class. But from the other hand, we can ask ourselves, so for example, okay, we have some negative results, we cannot do that, but what we actually can do. So are there any instances of a problem that can make us more happy, or something like that? And I want you to have a look at some stuff, nice stuff. We have no finite axiomatization of RRA, but we have kind of very useful and very intuitive instruments that would allow us characterize representable relational algebras. So we have some model theoretic techniques that would allow us to distinguish representable relational algebras from non-representable ones. Anyway, our negative results remain the same, but anyway, we can do something with relational algebras. So let me have a look at some definitions and explain them quite briefly. The first definition we need is the definition of a network. Networks, if very roughly, approximate a representation of a relational algebra if it's really representable. But for simplicity, we consider the simple case of this problem where our algebra, the first, is atomic, and the identity relation is an atom as well. Okay, so the first is to define a network, a pre-network. So let A be an atomic relational algebra where the identity relation is an atom as well, and a pre-network is a pair where N is a non-empty set of nodes, and L is a function that maps every pair of nodes to some atom. In other words, we have we have a directed graph, complete directed graph. That is, we have all edges. That is, we have an edge between every two nodes in both directions. We have loops and etc. So we have a directed graph where every edge is labeled with some atom of our relational algebra. But this is an arbitrary network, pre-network, but a pre-network is called a network if the labeling function satisfies the following three conditions. First, every loop is labeled by the identity relation, okay, and we have this connection if Lx, Lxy, and Lyz, as well as Lxz, are labeled with some atoms, and we have this requirement. Informally, this requirement means that our composition in our atomic algebra is a real relational composition. That is a composition of binary relations. That is, if we try to represent composition, then this composition behaves properly. So if C is labels Lxy's labels Lx. So let me reformulate that. If C labels the H xz, A labels the H xy, and B labels the H yz, then every such triangle or triple is consistent. It looks like categories enriched in at A. Yes, perhaps one may consider that as the instance of enriched categories, but one needs to check that precisely. Now, perhaps this analogy takes place, but I really don't know. That is so the third condition, the second, condition claims that we have a kind of transitivity for composition. So if xz belongs to the representation of C, then this is an element of a representation of A composed with B. Okay, does it make sense? Okay, and the third condition claims that if we take if we have some atom that labels xy, then its converse labels the h yx. So informally, so let me explain the intuition. If we managed to build a good network by an atomic relational algebra, then this algebra is representable because one may extract the representation from the labeling function, and we're gonna build those proper networks using back and forth games from model theory. Okay, does it make sense? Can I go ahead?
Yep.
Okay.
Yeah.
So the definition of a game. So let n is less than or equal to omega. That is, n is either natural number or omega. So we have a game with n rounds. It might be finite or it might be countable. That's why n is less than or equal to omega. And let A be an atomic relation algebra with the identity relation with, or to be more precise, with the one prime constant as an atom as well, and let n be a pre-network. We have two players, Abelard, he's a male, and Eloise, she, her, because she's a female. So we name these players after famous characters from the medieval philosophy. So those players, Abelard and Eloise, play a possibly infinite game, GN, IN, with n rounds, and during those rounds, sorry, this is a typo, they built pre-networks of array and n0, n1, and etc. And the game is played in the following way. Round 0, this is the trivial round. Eloise picks the initial network, which is given here, and the round n+1. Suppose a network has been played. So for all picks to atoms, A and B, and some nodes, X and Y, such that A, B, new elements, and such that A and B and L, Y, Z is inconsistent. And one may reformulate that in a more intuitive way, that L, X, Y is less than or equal to A composed with B by the property of atoms that follows from the Pearson law. Okay, and Eloise must respond with the pre-network n+1, which is extends the previous network with a node Z, and this node might be fresh with the following property, that L X Z is equal to A and L Z Y is equal to B. That is, we have a consistent triple, and this triple is consistent in our atomic algebra, and Eloise has to reflect this fact, the fact of being a consistent triple, using this labeling. But as I have already said, a labeling represents a kind of proper representation of the relational composition. Okay, and if all pre-networks being played are networks, that is, labeling function satisfies all those requirements, we had 3 conditions, then Eloise wins the game. Otherwise, Abelard wins. That is, Abelard wins if wins the game. I mean, if Eloise has no proper response for some consistent triple. That is, the situation when for all wins is the following. For all picks two atoms, two nodes, such that we have a consistent triple, but Eloise cannot provide a pre-network with these conditions, with these conditions by these atoms and these nodes. And intuitively, if not only intuitively, but the intuition is the following. If Eloise has a proper response during every round, then a given algebra, atomic relation algebra, is representable. Otherwise, if she has no proper response somewhere, then Abelard has a winning strategy. In fact, that is, our relation algebra is non-representable. Does it make sense? Do you have some comments? Does it look scary? Oh, sorry. I didn't want to hurt you.
Just a simple clarification question. So if Abelard or Eloise wins, then our algebra is representable or otherwise?
If Eloise wins the whole game, so we have n rounds, and Eloise always has a proper response, then an algebra is representable. But if she has no proper response somewhere, this is a finite round, then Abelard wins, and this is equivalent to the fact that a given relation algebra is not representable. That is, it cannot be materialized with some real binary relations. That's the moral.
Okay.
So can I go ahead?
Yep.
Okay. So we have the following fact. So let A be an atomic relation algebra. So if Eloise has a winning strategy in G omega dot A, then A is representable, where this dot is our initial network, which consists with one node with the only loop. This is a complete graph over the single edge, over the single vertex. I mean, a trivial direct graph, a trivial one element direct graph. That's what I mean by this dot. Okay, and the converse holds for finite algebras. But let's have a look at the proof sketch for the first item. So let us assume that we have an infinite game where Eloise has a proper response every time. That is, Abelard picks two atoms and two nodes such that we have some consistent triple, and we have an infinite game with infinite sequence of networks, and 0, which is our one element directed graph, and 1, the network which is constructed during round 1, and etc. So we have this sequence of increasing networks, and we put n to be union of all those networks which are constructed during all those rounds. The second item is to factorize nodes with the following equivalence relations. Where X is equivalent to Y if and only if it's labeled by 1, by the identity relation. Okay, the moral is we need that because during some rounds some elements might be repeated several times, and we factorize those elements whose edges by labeled by the identity relation. So this is a technical step. So, but this is a technical step, but this is an important step anyway. So let A be an element of a relational algebra, an arbitrary elements, not the only an atom, and we define this A with circumflex as pairs of X and Y up to the equivalence relations. So up to this equivalence relation, such that LXY is less than or equal to A. When we were discussing atomic relation algebras, I told you that every element of relation algebra, of an atomic relation algebra, can be viewed as a disjunction of atoms that A dominates. Let me remind you, I'm in this disjunction. So C is less than or equal to B, not A. This is a mistake. So B is a disjunction, and it might be infinite possibly. Then B is the disjunction of those atoms that which are beneath B. That is, we take all atoms that B dominates, okay, and take its supremum, okay. And here we repeat these ideas. That is, one may express an arbitrary elements of an atomic relation algebra as a disjunction of all those atoms, and apply this representation, this definition, and we have a representation for every element of a relation algebra. So in other words, we have this map that maps every A to A with circumflex, and so this is a representation of A, since all required triples are consistent. Triples which are extracted from the labeling function of a network. So we have consistent triangles, and the fact that all those triangles or triples are consistent is guaranteed by the presence of a winning strategy. So let me get back to this item. So Eloise has a winning strategy. Okay, we have this an equation for every vertices x, y, and z. So suppose we have C, an element of an algebra, B, an element of an algebra, and we have some elements of algebra A, B, and C, atoms for simplicity. And let me get back to this place. And if the pair X, Z belongs to the representation of C, then pairs X, Y belong, then the pair X, Y belong to the representation of A, and the pair Y, Z belong to the representation of B, if and only if C is less than or equal to A composed with B. That is, our consistent triangles, if very roughly, commute with relational composition defined on edges of the constructed network. That's the idea. Does it make sense? Or you need some clarifications or something like that?
I think we can move on. We can move on.
Go ahead. So, but before we go ahead, let me summarize what we discussed. We introduced the definition of a pre-network and the definition of a network. Networks approximate representations. Okay, and we have a step-by-step procedure of building networks if it's possible, and one can express this step-by-step procedure using a kind of back-and-forth game where we have some spoiler and duplicator. Abelard is a spoiler, and Eloise is a duplicator. Okay, and we have already seen that if duplicator has a winning strategy in the countable game, then a given atomic relation algebra is representable. That is, we have a kind of representability criterion for atomic relation algebras formulated in terms of games. The fascinating fact that we have games where we have the first player that picks some elements and the second player that responds with networks, and from this step-by-step game we can extract the representation of an algebra if and only if duplicator has a proper response. That is, for every 3 elements, if very roughly, Eloise can reflect them in terms of relational composition, that is, composition of binary relations. That's the idea. I've just reformulated all those results from this subsection where we have networks, games, and the way of extracting representations from the presence of a winning strategy. And we have the equivalence for finite relation algebras, and this allows us proven non-representability for some finite relation algebras. So I have already mentioned the Mckinsey algebra as an example of a non-representable algebra. And using this game, we show that Abelard can win the game of length 5, and this is equivalent to the fact that the Mckinsey algebra is non-representable. So we have, in fact, we have the representability criterion for relation algebras formulated in purely game theoretic terms. So let A be a finite algebra. So here we connect our games with models, but I decided to drop I decided to drop details and just formulate facts. And here is another typo. I'm sorry. There should be lambda I, where I is an element of omega. But never mind. Suppose we have a finite relation algebra, then there exists a countable set of first-order sentences such that A is representable if and only if those first-order sentences are valid in this algebra. That is, we have a countable sequence of first-order sentences, and this sequence is inductively constructed, and each of those sentences claims that Eloise has a proper response during the corresponding round. Okay, so we have the criterion. Let me remind you that an algebra is representable if and only if Eloise has a Venn strategy in a game with omega steps, and this is equivalent to the fact that we have a countable sequence of first-order sentences which are valid in this algebra if and only if this algebra is representable, if and only if Eloise has a winning strategy in the game G omega. And here one needs to reformulate the presence of a proper response in every finite round as a first-order sentence. And the infinite case of the same statement is also true, but this more complicated because this requires more advanced, more model theoretic kind of stuff, such as elementary chains and ultra products. So I decided to drop that as well. One may have a look at several papers to have more details about that kind of stuff, but a bit later. And here we have another fact, which is due to Robin Hirsch and Ian Hodkinson. And according to this fact, our array has a recursively enumerable axiomatization, with the axioms that encodes the presence of a winning strategy for Eloise, but in a bit more complicated game. But this game, such a game, is similar to those games formulated for atomic algebras, but not every. But generally, an arbitrary relation algebra doesn't have to be atomic. we need a more abstract version of a back and forth game in order to cover all possible representable relational algebras. But this fact is more complicated than the previous one, so I decided to formulate that as a fact. But one may have a look at the book called Relational Algebras by Games by Robin Hirsch and Ian Hodkinson. This one to extract very accurate proof of this fact. But let me finish with the non-representability of the Mckinsey algebra. Okay, so the Mckinsey algebra is an algebra which is generated by 4 atoms, 1 prime, and formally the identity relation, the converse of A. So here we assume that A, so we have A, the atom, and the converse of A. So these atoms are mutually converse, as in the case of the Points Algebra, and we have this atom called sharp, which is self-converse. That is, the converse of sharp is sharp. So that is, the operation of taking converses behaves on sharp as the identity function. So here we have the following set of consistent triangles: X, X, the converse of X, and the identity, and A, the converse of A. So that is, Mckinsey algebra extends the Points algebra, but with the additional condition. So if we forget about this atom and consider the subalgebra of the Mckinsey algebra, then we will have the Points algebra, the algebra of relations on the set of rational numbers. But we have the additional consistent triples as the percent transforms of these ones. That is, sharp is less than or equal to A composed with its converse, and the rest ones are explained similarly. And one may permute them using those triangles that I visualized earlier. So let us show that Abelard has a hidden strategy in the game G5, where the initial network is a one-element directed graph, and we play on atoms of the Mckinsey algebra. So one may provide a concrete game where Eloise has no proper response during some finite rounds of this back and forth game. So here are some pictures. Round 0, B0, that's the same as dots from the previous slide. And here we have the initial position with the loop B0, B0. So round 0 is trivial. So round 1. Here we assume that B0 and B1 belong to the representation of sharp. That is, so I decided to drop the details of a game and discuss only what we have in terms of representations. That will be a little bit more simple. So suppose B0 and B1 belong to the representation of sharp. And we suppose for contradiction that we have some representation of the Mckinsey algebra. So suppose we have some representation of the Mckinsey algebra, then we have some elements B0, B1 that belongs to the representation of sharp. And we formulated this fact in round 1. Round 2, we have a consistent triple. A, the converse of A, and sharp. That is, sharp is less than or equal to A composed with its converse. So this is a consistent triple. Okay, so we have some C, B0, and C, B1 that belong to the representation of A. Okay. That is, let me reformulate that. We have B1, B0, B1, a pair that belongs to the representation of sharp, but A, the converse of A, sharp, is a consistent triple by our definition, this one. So we have C, B0, that belongs to the representation of A, and we have B1, C, that, and we have B1, C, that belongs to the representation of the converse of A, but that's the same as C, B1 belongs to the representation of A. Okay? That follows from the definition of representation plus the fact that this triple is inconsistent. But I remind you that the fact of being consistent is equivalent to sharp is less than or equal to A composed with the converse of A. Okay. So here we have this triangle where B0, B1 belong to the representation of sharp, and C, B0 and C, B1 belong to the representation of A. Okay. Okay.
By the way, it's just a question. Later we have said that the sharp is closed and the converse. So B1, B0 is there should be representation of sharp too. Am I right?
That's correct, but we actually don't need that. So yes, but you're right. We assume that we have some representation of the Mckinsey algebra in order to have a contradiction. But if B0 and B1 belongs to the representation of sharp, then B1, B0 belongs to the representation of sharp as well, because sharp is self-converse. The converse of sharp is equal to sharp. Okay. Do you have some questions related to round 2? Or it's quite clear? Or can I go ahead? Can I explain round 3? Okay. So we have another consistent triple. The converse of A and sharp. That is, sharp is is less than or equal to the converse of A composed with A. So we have some B0D and B1D that belong to the representation of A. So here is B1D, and here is B0D. Okay. A friend of mine has left us, but all right. So we obtain these pairs from the fact that we have a consistent triple, the converse of A, and sharp. Okay, does it make sense? So if B0D and B1D belong to the representation of A, so does CD. That is, the pair CD also belongs to the representation of A, because this pair is this triple is consistent. That is, A is less than or equal to A composed with itself. Okay, so we have CD because we have B1D and we have CB1, CB1, B1D composition. A is a subrelation of the composition A with itself. So one may forget about B1 and take a pair CD. And the result of this round 3, that CD belongs to the representation of A. Does it make sense? So we have another consistent triple, A sharp sharp. That is, sharp is less than or equal to A composed with A. So that is, there exists some A such that C, E, and ED belong to the representation of sharp, because sharp is less than or equal to A composed with sharp. Okay, and we take C and D from the representation of A. That was the result of round 3. Okay, but sharp is a subrelation of A composed with sharp. So if we have, that is, if we have some elements of that is, we have some A such that C, E, and ED belong to the representation of sharp. That's the idea. So by transitivity, if roughly B0A represents X and B1A represents Y for some elements of K, but for some atoms of K, that follows from the definition of representation, in particular representation of composition. So we have these additional lines. So let me repeat that. B0E represents X, B1A represent y for some atoms of K of the Mckinsey algebra. Okay, but xy, but we have the only choice for Eloise, where x is equal to sharp and y is equal to sharp. So let's have a look at this diagram. We have a pair CE and the pair ED, okay, such that, and those pairs belong to the representation of sharp, okay, we have B0E and B1E, that is this elements, and we have to label these edges B0E and B1E with some elements in order to make triangles CEB1 and DB1E and etc. consistent. But the only choice to make those triangles consistent is to put is to define x and y as sharp. That is, x is equal to sharp as well as y. So we have the only choice. We have no alternatives. But if we had the proper response and label these edges B1E and B0E with sharp. So if that was a proper response, but then that would imply that the triple sharp 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 is consistent, but that's not the case. So this is the idea. This triple of atoms is forbidden. We have no this triple sharp 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 in the list of good triples of atoms. But if we had some representation of the Mckinsey algebra, then that would imply that sharp is less than or equal to sharp to compose with itself, but that's not true in the Mckinsey algebra. But from the and that leads to contradiction. We assumed that we have some representation of the Mckinsey algebra, but in our representability game, Abelard has a winning strategy because he's managed to provide bad atoms of the Mckinsey algebra such that Eloise has no proper response. And that makes the Mckinsey algebra non-representable. That is, it cannot be materialized with some binary relations. This is an abstract relation algebra that base the axioms of relation algebras, but it cannot be represented with binary relations. That's what I wanted to say regarding the Mckinsey algebra. Do you have some questions? I tried to explain this construction in a gentle way. I hope I've managed to do that. But if you have more remarks, please do ask some questions. as far as I can see, this part of the talk is a little bit more complicated than the first one. Yes, this kind of stuff is a little bit more advanced because this requires model theory, representations. We have some model theoretic techniques to extract some algebraic constructions, but this is it. This is algebraic logic. So it's this is a complicated discipline, and that's what we algebraic logicians do every day, every time. We build representations using such games. If we are interested in relational algebras, but relational algebras might look quite difficult to study, but please believe me that cylindric algebras, algebras of higher order relations, well, relational algebras and cylindric algebras are cousins, and we have the same results about cylindric algebras. So replace relation with the cylindric, and we have the same story, but representability games for cylindric algebras are more complicated, but the idea is similar. But in the case of cylindric algebras, the definition of a network is a little bit more intuitive, because cylindric networks are closer to model logics. It's closer to a version of S5 frames, but this is a different story. But let me summarize. What we discussed during this Friday and last Friday. First, Boolean algebras and the way of materialization of Boolean algebras with some algebras of sets, algebras defined on ultrafilters. Second, we have Boolean algebras with operators. This is a kind of algebraic counterpart of model logics. After that, we had a look at relational algebras, representable and non-representable. And we also had a look at one of results related to the characterization of representable relational algebras using games. But I decided to discuss one of the most simple results, where algebras are atomic, and because we have a more simple definition of a game in that case. That is, we characterized representable atomic relational algebras, and finally we had a look at the example of a non-representable relational algebras, and we proved that this algebra is non-representable using those atomic games. I mean, games on some atomic relational algebra. In this case, that atomic relation algebra was the Mckinsey algebra. As far as I know, this is the smallest example of a non-representable algebra, but I could be wrong here. Finally, let's have a look at some references. I guess you know about the book by Blackburn, De Rijk, and Venema. Previously, we were discussing complex algebras, algebras that obtains from cryptoframes. If you are interested in that kind of stuff, I mean, the connection between algebraic and relational semantics of model logic, Then you may have a look at the paper by Robert Goblet about complex algebras and varieties of complex algebras. This is an algebraic counterpart of the definition of a cryptic complete model logic. In fact, I've already said that representability is not decidable of finite relational algebras, and this is the result by Robin Hirsch and Hodgkinson. And I used this book mostly, written by Robin and Anne as well. The book's called Relational Algebras by Games. Again, that one, can you see that? And relational algebras and binary and cylindrical algebras can be used in proving that products of model logics are not finitely axiomatizable. And here is an example of a curious paper written by Robin Hirsch and Hodgkinson and Agikurush, and they showed that model logics between K products K and S5 times S5, that is three-dimensional model logics, are not finitely axiomatizable. And they proved that using some techniques related to representability games on for relational algebras. A quite curious paper. This paper is about the questions of canonicity, canonical varieties with no canonical axiomatization. As you might know, there are examples of canonical model logics that cannot be axiomatized with the canonical formulas. For example, K4.1 transitivity plus the Mckinsey axiom or something like that. And there are more examples of Boolean algebras with operators with similar properties. Their varieties are closed under canonical extensions, but it cannot be axiomatized with the canonical identities. Well, very roughly, canonical identity is the same as a canonical formula, but formulated in terms of universal algebra. And this is a survey of Boolean algebras with operators, and here is the classical paper about Boolean algebras with operators written by Johnson and Tarski, and they proved their representation theorem for Boolean algebras with operators in exactly that paper, written in 1951. This paper contains some examples of representable relational algebras. This paper is by Donald Monk. He was a student of Alfred Tarski, and this is a paper by Venema where he considers some examples of Boolean algebras with operators that cannot be axiomatized with the Sahlqvist equations. And again, the Sahlqvist equation is the same as a Sahlqvist formula, but formulated again in terms of universal algebra, in terms of Boolean algebras with operators. And in particular, Venema proved that the class of representable relational algebras cannot be axiomatized with Sahlqvist equations. So if we consider the class of relation, so if we consider the equational theory of representable relational algebras as a kind of model logic, where we have a binary modality composition, a kind of binary modality, because this is a operator, a kind of binary diamonds. We discussed that last Friday. Then as a model logic, the equational theory of our array is canonical, but it's not Salquist, it's undecidable, and etc. But it's canonical, that is, it is cryptic complete. As you might know, canonicity implies cryptic completeness, so the equational theory of representable relational algebras is complete as a kind of model logic. That's the moral of all those results related to canonicity and Salquist axiomatizability. And this is it. That was my last slide. So many thanks indeed for your attention. And if you have